In previous streams, we have got this to talk a little bit of CAN, kind of, maybe. And today we're going to carry that on. Hey, Mount Joy Guitar, and hey, QNXB as well. Oh, and hi, Rod as well. Hi, lots of people. So this is a Glasgow CAN add-on board that I designed a little while ago on stream, and we've been working on the gateware for a bit. It's been a little bit slow going, which has been frustrating, but I think that's partly to do with my mental capacity at the moment. So what we have is a Glasgow on the right-hand side here, and then we just got a standard ribbon cable that brings it to the CAN add-on board, which provides 2 channels. And then here I have a CAN USB interface that I made a while ago, and I've also got a third CAN device on the network as well down these wires, which will sit on the network and acknowledge the packets as well. In terms of what we're doing is going to be primarily playing with gateware. So in previous streams we have we've worked towards getting the low-level CAN interface working, so getting the raw bits through. We have then continued on to get the bit stuffing handling, so that should all be happening now correctly. And now I think we're in a reasonably good position to actually frame the packet or the message and feed that up to the PC to decode it. So I'd like to do that first, I think, is to get the framing correct and push it up to the PC. I'd also quite like to get the CRC happening on the FPGA. I was having a rummage earlier today to sort of remind myself about CRCs and how they go together. But I'm not sure I've got it in me to do it on stream unless there are people who might like to help. So do chip in if you have some ideas about CRCs and how they work. So I didn't tidy this up from the last episode or last stream. Let's just have a quick look through. So we got at the top, we got the CAN bus, and that just deals with connecting everything to the physical pins. We've also got a debug pin that we're using to put things on the scope so that we can see timings and that kind of stuff. Currently we're working with a fixed 250 kbit per second bus, and that comes to about 4 microseconds per bit. And because of the time contour that we've covered in detail previously, I'll just grab the CAN bus wiki page back. Here it is. So the bit timing, or the time contour, whatever you want to call it, means that you have this separate period. So normally with a UART, for example, you'd sample at about 50%, but in CAN you sample a little bit later than that for various reasons on the bus. The CAN USB interface is not really available, and it uses some software that I've written in sort of my work, with my work hat on. It is something that I was wondering about making into a product, so if you're interested, then certainly let's sort of think about that a bit harder. It's an STM32F105 with 2 CAN interfaces, a USB connector, and then this runs Zephyr, which is an RTOS, and then on the other side I've got a Linux kernel module which brings those 2 interfaces out into real CAN interfaces on the PC or on whatever else you're using. Okay, so there's the bit timing. We've dealt with the plain bits, so that's good. And we've also now dealt with the bit stuffing, which is outlined here. So these pink bits are to prevent the bus from getting stuck or being in the same state for too long. You have to insert a stuffed bit. And so after 5 bits of the same value, you have to insert a stuffed bit of the opposite value and then continue. So we need to, on the receive end, which is what we're doing at the moment, we're just sniffing, we need to correctly spot and remove those from the stream. So coming back to the code, we've got the timing all outlined here, which is good, and that's been working nicely. And then we've got a state machine. And this will run through the bits and pass them up, I believe, and then this sub-target will then take the bits on the trigger and feed them into the FIFO. So that's kind of where we're going to be looking now. I think this is pretty much good to go. It just needs tidying up. So I haven't done that yet because I'm lazy. So here is, this is Glasgow running up here, and then down here we've just got CAN send, which is a standard Linux utility to put messages onto a CAN bus. So if I bring back the scope, you can see that if I send a CAN message, we get the data comes through and it's also visible on the bus. I can put some space in there. I can do let's do 55AA, 55AA, for example. And you can see on the scope, we then have the data coming through. If I wiggle between 55 and 55AA, there we go. And then looking at the output of Glasgow, what we see is the 555, so these 2 bytes are the ID of the message, and then everything kind of goes to pop. And I think that's because we are not correctly counting things still. So let's have a look, see if we've got the bit stuffing handled correctly, or if maybe something else is going on with bit counting. I suspect we got all sorts of problems because we only got as far as the ID previously. Okay. Just reminding myself about the code then. We got this debug pin here, which will be set high while we're in the arbitration ID. The debug arbitration signal is then put out onto pin 9. So if I hop that over onto pin 9 like that, rerun, then the blue trace on the scope should be high for the duration of the ID. And you can see it's high, but then it goes low and then it goes high again. So that's not correct. Let's see what's going on there. We come out of here. Oh, right. Okay. So this is exactly the problem. We're just returning to idle immediately, and that's not correct. So we're getting the arbitration ID correctly to the host, but then we're just returning to idle, and actually we need to be moving on to the next part of the frame. So if we look here, we got arbitration is 11 bits, and then we've got the remote request bit, and then we've got the extended ID and a reserved bit. And we're just going to expect them to both be 0 at the moment. The remote request we can kind of ignore, I think, probably pass up to the host. And then finally we get onto the DLC, which is the payload length. And that has a valid value of 0 to 8, I think it is. And that controls the length of this data field in bytes. It is a 4-bit value, but you can't legally have a value higher than 8 there, which is, yeah, it's an odd one, but there we go. Okay, so after we've got the arbitration ID and passed that up, we need to be moving on to the arbitration remote field. And on this RX ready flag, or strobe, pulse, whatever you want to call it, we should sample the line to see the arbitration remote field flag. Now this is something we cleaned up. We got rid of a lot of these values. I think the idea being that we're just going to put them into like a FIFO type shift register, and then send them up to the host. So it is the remote request flag, the ID, and the reserved, I think, should go into one package and then get up to the host. Actually, we can get all 3 of those and all 4 of the data length field into 1 octet, 1 byte, and send that up to the host. So if we now count for 7 bits, let's call this arb and control, arbitration control. we want to count for 8 bits. And to do that, we need to set the MD sync counter equals to 8, I believe. Yes. No, sorry, 7 bits, not 8 bits. So in here, we then need to decrement that each time. And we should also then check to see if it's 0 and move on to the next state. So we're going to send the data up. Oops. That needs to be an ND comb combinational logic. And that gets written to the FIFO back to the host. Nope. There you go. If anyone has any questions, please feel free to ask or comments, or if you'd like to point out that I mistyped or I'm doing something silly, please do. Okay, now actually what we're doing here is we're only passing up 7 bits. So it'd be sensible now to actually put a 0, fix 0 on the front of that to make it into 8. So to do that, we can use cat, and I think we can do const 0 unsigned 1 with the 0 to 7. Let's just remind ourselves the RX data is a sort of rolling shift register inside the, you can't see that, inside the low level. It's 32 bits. And what we want to do is have the most recent 7 bits, I think. Yeah, so the new data comes into the bottom of it. So I think that should give us that nicely. Let's just for now go back to idle. So now we should be able to have the ID and also the rest of the arbitration and control fields come through. So we've got these 7 bits here. So let's just run that again. And if we watch the scope, we should hopefully see that blue trace goes low for a longer period. So it'll remain high for the ID, and then it'll go low for the next 8 bits, and then it'll probably do its sort of out of spec or incorrect stuff after that. And what do we see? Yeah, it doesn't look like it went low. Not for longer, at least. Is that triggering? It is triggering. Okay. Let's just get some space in here. We can see our 555, which is this. And then what we're doing is we are sending a 0, 0, 0 and a DLC of 4. So that'll be 0, 1, 0, 0. So that'll be 0, 0, 0 and 0, 1, 0, 0. 1, 2, 4, yeah. And that X is the bit that we're filling ourselves with a forced 0. So the fact that we see an AA is not correct. And the fact that on the scope we see that blue signal sort of goes straight high again is also not correct. So let's have a look at that. Okay, don't see the reasoning there. Let's just try running it again, see if that helps. Don't think it would, but give it a go. We're still saying AA00, and that is incorrect. What I'm going to do, I think, is to turn off this so we never see the ID anymore. We should just see the first field being the remains of the control and arbitration fields. So the first thing we get through should be not AA. Okay, now if we change this, do you reckon we get some other data? So if we change that for 5.5, no, it's just fixed at AA. Okay. Let's put a known value in here. 3.4. Just to make sure we're in the correct state. Okay. We see lots of 3.4s. That is a little bit unexpected. No, it's probably okay actually. Just thinking about what's actually going on here. So we do actually enter that state, which is good. The counter gets all the way to 0. Oh, silly me. We are missing the strobe that we need to watch out for. That means that every cycle of the 48 megahertz clock we are going to be running on. That is not the thing to be doing right now. Okay, that looks a little bit better perhaps. Let's put the real data back in. Like that. Again, the first byte is the only one to consider at the moment, just because the rest of it's going to be garbage. It's going to be resynchronizing on not the right stuff. There we go, 1.0. Is that what we expect? No. What did we expect? Ooh, okay. If I make this only a 0 byte frame, do I need a final hash in there? 1.0, 1, 2. Oh, 3, 4, 5, 6. Okay, so we got 0 to 8C for a 0, 1, 2, 3 payload length. And if we do the 4 as well, we get 1.0 again. Now if we write them down, what does that actually look like? We've got a 0 is a 0 byte, and then a 2 is a 1, 8 is a 2, and 1.0, so O again is a 4. These come out to be that and that and that. 1, 2, yeah, and 1, 2, 4, 8. Okay, that's unexpected. Looks like we're getting 2 shifts in there when we shouldn't be seeing 2 shifts. Let's perhaps put this just to the first 8 bits again. I suspect my cat is upside down. I was getting that horrifically backwards last time. Tell you what, in here, in the applet, I'm going to add a new task, async task, which will just print out stuff to separate data out. I'm going to call it spacer. Need to remember how to make a new async task. Async create task, simple. And that hopefully will just put dashes in every half second. There we go. Okay, so that's a 01, that's 04, 08, 06, 08. This is not right. 14868. What does the scope look like? The scope looks reasonably good, actually. I'm going to need to pull up my own view of this because the other screen is a little bit too small for me to see. So that does actually look like that's correct. Are we counting too many bits? Do we think that's what it is? So here we set counter to 11, and we then count down, we trip at 8 and trip at 0. So 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. I think that's okay. If we then set this for 7, 7, 6, 5, 4, 3, 2, 1, 0. Oops. Actually related to the next state. Let's just put a space in there. Okay, I think that yes, the cat was backwards, but I don't think cat like that. I don't think that's going to resolve it though. What do we see? 0, 1. 4, 8, 6, 8. Yeah, this is not correct, is it? I think perhaps looking a little bit closer on the scope might be a good idea. Let's do that. Let's trigger on the falling edge of blue, and then let's try and get a 1 bit per period coming out of that. What do I say? A bit is about how big? Ish. There you do. Okay. So now we can hopefully see a little bit better what's going on. So if we do a 5.5 with 0 payload length, oh, it's gone off in the screen. Oh, of course, because we need to hold off on the trigger for, I don't know, do 10 milliseconds-ish. Is that going to help us? It's still the DLC, but it's still off the end of the screen. So that's 4 microseconds. Let's go for 8 microseconds. So that'll be 2 bits per graticule division. Like that. Okay. Now what we have here is we've got a single bit. So 1, 2, 3, 4, 5. 4 of those are the grab this back. So I'm going to bring these together now. Turn off that one. Hopefully you can see my mouse cursor on here, okay? So we end the arbitration ID and then head into these 7 bits. Now because it is an arbitration ID, 55 ends in a 0, so that's 1 0, and then we've got 2, 3, 4, 5, and then we have a stuffed bit, and we got 1, 2, 3, 4, 5, 6, etc. So what we actually have in terms of the data layout is a request remote, an ID extended bit, reserved, and then we've got the DLC is 0, 0, 0, 1. Is that correct? Is this falling too late? It'd be nice if the scope actually bounded these fields a bit more clearly, wouldn't it? No, that is correct. So that is a 5-5 on the front of that. Shift this over a bit. Let's re-trigger that. So there's the end of the 5. 5, 5, end. We got, let's draw on this. It's going to be much easier, isn't it? Grab this up. Okay. So we have 5, 5. So that's the end of that. Whoop. And then we have the remote request, and then the extended ID, and then the reserved bit. I'm just going to draw a squiggle in there. That's reserved. This is then a 5. And then we've got the data length DLC. So that would be a bit stuffing issue. Yeah, potentially. That's kind of what I'm thinking. So we've got DLC here of 0, and that's a stuff bit. And then we've got 0, 0, 1, which is unexpected because even the scope decodes us as a DLC equals 0. How does that marry up with what Glasgow sees? Does Glasgow see a 1? Because if it does, then it's reading the same as us. It does see a 1, okay. So that means that we are reading this wrong. What's special about the DLC then, hey? Let's put request remote in there just to clarify this in the brain. Make it red. Oops. That's that there. And then we've got the ID extended. Is there. We've got the reserved bit, ignore that. And then we've got the DLC. And the DLC should be 1, not that, 2, 3, 4, up to there. Am I being silly here? Let us read some specs. We've got the CAN PDF here. Message framing, is that in here somewhere? Data frame, arbitration control data. The data field can be of length 0, that's good. The remote request is, yeah, so that's directly after the 11-bit ID. That's okay. Control field consists of 6 bits, includes the data length code and the 2 bits reserved for future expansion. The reserved bits have to be set dominant. Receivers expect dominant and recessive bits in all combinations. The data length code, a number of bytes in the field, is indicated by DLC. This is 4 bits wide and transmitted within the control field. Yeah. There it is. Reserved, reserved, length, 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 length. So the fact that we've got the extended ID bit is kind of extension of the spec that is clearly old and out of date. And there's the DLC. They are still stuffing this, so it's not like we shouldn't be stuffing it. And even if we didn't stuff it, we'd be reading that wrong. I do suspect, I'm afraid, that all of these things are in the wrong place. I think we need to shift all of this 1 bit left. Not going to work well. Which would make that a 0. These bits shift as well, obviously. That stuff bit doesn't shift, just these ones. What does that mean though? That means that this 5 is surely not right. This is annoying. Oops, I made it crash. Hold on, never mind. Lost our drawings. Let's bring that back. Let's put in. So that is a 0 length. We put a 1 length. Oops. You see that? It shifts. I run this a couple of times, so I'm going to do a new length. Length of 1. That's in line, and then it shifts 1 bit. So I think something wonky is going on there. And if we run the Glasgow Applet, first time we get, yeah, different value. Oh no. So if we do a 1 length, we get a 4, and then we get 2, and then we get 2, 2, 2, 2. And if we do a 2 length, we get a 4, and then we get a 4. Okay. 3 length, 6, 6, 6, 6. 8, 8, 8, 8. 2, 1 is a 2 and then a 2, okay. We get a 1 and then a 3, so that's not stable. Is this because we're not framing it correctly? do we actually need to wait for a timeout here and let it stay low for a long period? Would it be worth sending a debug signal on a stuffed bit to rule out issues there? Yes, let's do that. No harm. Let's add that. So we've got two debug signals that we're outputting. I need to remember what they are. Here they are. They're in the pads. Here. Debug SP. Let's use that. Debug SP. That's L debug. Oops. Oh, come here. There we go. So that's looking for stable count is 4. So that is a stuffed bit. Oops. Let's put that to 5, and then I think that should indicate stuffed bits for us. I will move this over back to that signal. Okay, what do we see now? Oh dear. Let's go and push the magic button. That is a low. Do we see anything at all? No. Is this because it's either so small that we can't see it, or something else? I pull the nose off the probe. Is it connected to the right pin? Is. Let's trigger back on CAN again. I'm sure we saw something earlier on this, didn't we? That's 8 microseconds at -7. Oh, I've got to turn that off. There we go, so there's our message, and there are some pulses. Why wasn't that triggering then? Bizarre. Going through the hold off, maybe, I don't know. Never mind. So this should identify the stuffed bits for us. So if we get this to 8 microseconds, that should be 2 bits per gratical frame. There we go, and that 5.5 there is the ID. Okay. So that should be fairly stable for us. I wasn't expecting that. Is it triggering again? Oh, it's on edge trigger, sorry. Okay, there we go. That should be good. There we go. Okay. So that indicates a stuffed bit. And if we do just a 5.5 with 0 byte payload, bring this back, we have the shift that over 1/2 bit, or 1/2 gratical. Oops. Okay. What we have then is the ID here. And then we've got to, I don't remember what it was now. I'm gonna put this on the other screen so I can keep watching it. Yeah, so that, and that. So this is the request remote, this is the extended ID, and this is then the reserved bit. And then we've got That's correct now. That's the 0000 DLC. So why is that correct? Okay. If I then put that back up and I'll move that over there. If I then put this to a 0 length packet, it comes out like that, which is correct. If I did a 1 length frame, that looks correct. A 2 length, that also looks correct. And then a 3 length, the bit stuff should shift, I think. Oh no, sorry, with a 4 length, the bit stuff will shift. Like that. Yes. Okay, so I think that all looks good. I'll draw in another picture quickly. So we have the ID here. We've then got the remote request and the extended bit followed by the reserved. And then we've got the DLC, which is 1, 2, 3, 4. Halfway through there. That's a 0, 1, 0, 0. And that is, of course, 4. That's good. Now let us keep these pictures, put this back on the other pin, run the same thing again. What have I done? Hello? There we go. Don't know what was going on there. Okay. Now, let's refer to our other picture. These should be the same. And this blue line up here should mark the end of the arbitration and the control field. So I'll draw roughly down there. I'm going to make that red because you can't see it otherwise. And down there. So yes, okay. It's slightly shifted out of phase because of the sample point. But we have the 5 there. And then got 1, 2, 3. So that's the reserved. And then we've got the 4 bits. 1, 2, 3, 4. Actually, there's 5 bits there. So could that be part of the issue? That we are actually counting too many bits through. That will shift everything up 1. That's an 8. That's a 6. That's a 4. That's a 2. Yeah, that is shifted up 1, isn't it? That's a 1. Oh, and that's a 3. Okay, so ignore that. That's something going wrong there. Okay, with a length of 1, we have a 2. With a length of 2, we have a 4, 6, 8. And so that is 1 bit shifted out. So this needs to be a 6, perhaps. I really hate these off by 1 type errors. I just can't reason about them in my head, unfortunately. Let's get the scope back. So now if I send a 1 byte frame, scope says this, and we get a 1. Look at that. If I send a 2 byte frame, I get a 4 and then a 2, okay, and then a 4 and then a 2 and then a 4 and then a 2. So yeah, so we've got to be careful with our framing. 3 byte, we get a 3 and then a 3 and then a 3. 4 byte, 4, 4, 4. 5, 5, 5. Oops, 6, 6, 6. 7, 7, 7. Syntax of the utility, yeah, so the ID and then a hash and then the bytes separated by dots of the payload. So this is a 7 byte payload addressed to ID 555. If we do that, and we get an 8 byte payload, which is good. And if we go all the way down to 0, we get 0, 0, 0. Okay. So I think part of the issue we have now is that actually we're saying go back to idle, but then it's re-triggering itself and getting sort of, it started counting again. But actually perhaps what we want to do is idle wait instead. And that will then actually wait for the line to go idle for a duration instead. So in here, I think if we could just count for a big number. How big is the counter? Or we could watch until the line goes idle. Count is 32 bits. Okay, let's just count for a big number. How many bit times do we want? Go for 128-ish. That's a really lazy way of doing an idle counter. And that should give us stable output now on here. Okey-dokey, so 0, 0, 0, yes, look at that. Okay, 1 byte frame, 1, 1, 1. 2 bytes, oh, okay. That looks good. Okay, cool. Next. That was painful. I'm sorry, everybody. Right, now in here we have the payload length, and that is really crucial for our next state. So we need to pull that out. And I think if we do m.d.sync, and we probably need a new variable for that. Let's go for... Oh, we already got one. Control DLC. DLC equals, and if we take Rx data 0 through 4, 0 through 3, is that inclusive? We want the first 4 bits. That's how you do it, isn't it? And that then means that we need to take the counter needs 8 bits. And we then move on. Data. We're going to throw up a word at a time, 8 bits, 0 through 8 to the computer, and then we need to decrement the DLC. Control DLC equals -1. If we reach 0, we then go on to the idle wait and say if it's greater than 0, we need to continue. Is that all we do? Yeah, I think so. In that case, I'm actually going to say if it's equal 0. Idle wait. Okay, now we should get the data through. Do you reckon it's going to be that easy? Oh, broken. Data is already defined. Need to delete it. Let's get rid of all this. I think it's wrong and old and tired. Kind of hate deleting code. Ooh. I'm just gonna comment it out like that. It's not really a comment, but whatever. Idle wait. There we go. Yeah, unexpected indent, of course. What do we reckon? Okay, 0 bytes. We should get a 0 followed by no data. Or we get 9D. That's the checksum, I think. No, that is actually incorrect. We shouldn't get the 9D. So we need to actually... This is going to be our off by 1 type issue again, isn't it? So we need to, instead of storing that, we need to store that -1. Okay. Ooh, unexpected. Why are we still getting a 9D? Hey Omni, how you doing? Oh. We also need to do this. The doom of CAN. I'm glad you're okay. We are just trying to break up all the fields and get them into the computer at the moment. I think, to be honest, it's struggling mostly with my off by 1 type reasoning, or failure to reason. So at the moment we are expecting 0 bytes of data and we're getting a unexpected byte through, which is incorrect. Oh, lots of data there. I haven't got my silly RX notes, so that's okay. 128 divided by 8 is 16. How many is that? Oh, it's gone off the top of the screen now. Is that 16? No, it's 14, 15, 16. Okay. So those two are probably CRC, and then this is idle state. But I wasn't expecting to see data from them. Bonus bytes indeed. Don't look at the bytes. Pretend they're not there, it'll be fine. Right. That will take bit 0 through 3. Occasionally things happen, yeah. I'd like to avoid that if possible. Aha, okay, part of this problem is that with 0, we're going to go through and do all of this stuff before realizing it's 0 and realizing that we don't need a data state. So actually in here we need to say if the RX data is 0, just skip it. The big numbers being written twice. What are you referring to there? Any mouse? In the can send command, let's go and have a look at that in a sec. I just want to finish this while it's in my brain. 2 idle weight in it, just to push that away. Okay, and this can send command down here. Can you read that okay? I shall make it a bit bigger. Basically, what we have is the Linux can send tool. And it takes this format here. Yeah. So what we can do is send the CAN ID, so that's 555, followed by a hash, and then we can send the data that we want to transmit. And that can be from 0 bytes, so just nothing, to 8 bytes. So if we do 1, 2, 3, 4, 5, 6, 7, 8, each of these is a byte, and it's separated by a dot just to sort of aid clarity and readability, I guess. So some of the examples we got down here, this one, for example, they've omitted the dots, so we could insert dots here, and it would get the same result. And the address there is a 5A1 instead of 555 like we're using. So I hope that makes sense. Hopefully I'm talking about what you're talking about as well. No worries. Okay, now then, if Rx data, so the first 4 bits are the length, and if that is equal to 0, we're just going to skip over the data period or the data state. If it's anything else, that implies that it's got some data. We should probably do some kind of catch for if it's greater than 8. Greater than 8, then we need to say it's illegal. And then finally we then say, actually, if it's between 1 and 8, confuse bits and bytes. Oh, no worries. If it's between 1 and 8, then we say how many bytes we want to capture, and we set this up, the counter ready for 8 bits per word, and then we move on to the data state. So that looks good. In here then, every time we get the Rx ready pulse, we decrement the counter. If that counter is equal to 0, we then share that data with the host. We decrement the DLC value, and if this is still greater than 0, we reset the counter to 8, wait for the next word to come in. Otherwise, if the DLC counter has reached 0, we then move on to the idle wait. I feel like there's still an off by 1 error in there, but we shall see. CAN-FD can come later, much later. We're getting some pretty erratic data out of this, aren't we? I feel like I'm going down the wrong path again. That off by 1 error I referred to just now, that is in this bit here, so let's put 7s in that. I feel like that. Oh, guessing, isn't it, at this point? Changing numbers and see if it just sort of falls into place. Ah, look at that. Perfect. So 0 bytes and we get garbage because, I don't know, we wanted to look into that. There we go. 1 byte, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay, the application actually deals with that for us, and it doesn't let you send more than 8 bytes. It means we can't test that, but I think it'll work. Let's put greater than 7, and that will then catch the 8-byte case. As it should quite, yeah. There we go, okay. No data state, 8. Okie dokie. So now there's something going on with the 0 length. Oh, I think I know what it is. I'm doing -1, aren't I? Where's that -1? The -1 is here. Oh, okay. Yeah, they shouldn't let you put a number bigger than 8 in that field. And that's fine that the application takes care of that for us. No worries there. Meanwhile, we have this issue where if we send 0 bytes, we actually get that many through. And that makes 16. Okay, so we are seeing 16 bytes where we don't want them. 16 is a 4-bit number that's all ones, which implies that it's actually coming into this bit. But it should be caught by this bit, right? Need some Glasgows to do that. Exactly, yeah. Put some illegal states on the bus. Hold it high, hold it low, etc. Violate the bit stuffing schema. Oh, we've got an if, and then an else. That should be an elif. Oh. Yay! Okay. That's better. Okie dokie. Let's add in our ID again. Oops. By 500. That's brilliant. Okay. So that means that we have done all of that. Now is the interesting bit, and that's the CRC. All of this, that's 8 bytes there. 1, 2, 3, 4, 5, 6, 7, 8. And that then leaves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's not a square number of bytes. And I don't quite know how the CRC deals with this. I haven't even got a CRC doodad going yet. This is something that I was hoping we might get to today, but I also feel like I need to do reading to remember how to do it. CRC is 15 bits, followed by delem, followed by an acknowledgement, followed by the end of frame, and then interframe separator. So this means that now that we've done the data, we need to capture the CRC. That's 2 bytes worth-ish, 1 bit less than. So these idle weights turn into CRC. It is a weird length, yeah, but meh. CRC. So there are 3 points which we can go into the CRC. This is illegal, so I'm not going to do it there. So that's only 2 points. CRC is 15 bits, so if we refer back to the very beginning, the idle, when it gets the trigger, we're setting it to 11. And that covers the full ID. Does it also cover the starter frame? Is that why it's 11? Is it actually 10 plus 1? Okay, that's starting to make a bit more sense. In here then we need to do md sync for the counter equals, what was it, 15 bits? Yes, so 14. Need to do that again down here. Excuse me. Okay. Because we have effectively 2 bytes, we can do the first at 8, and we can then pad it out. So that's just like the ID field that we're doing over here. Actually, I'm just going to copy that because it's so close to what we want. What we want, though, is not 0 through 3, it's 0 through 7. Or 0 through 6, sorry. And we then need a 1-bit padding. Okay, and then we can continue here and do the final state, which is the last one, the 8. The 0, sorry. And that is the full width. So that's just 8. Like this. And that's then when we step on to the next state. What do you reckon? What do you reckon? Let's get the scope back. And let's get a full frame on screen again. So this will show us the CRC on the scope. And if we run that, we get a CRC of 674C. 674C, look at that. Well, that's very nice, isn't it? And that would be 3B93. Brilliant. CRC is easy. Okay, now we've got to actually calculate it on the Glasgow. And verify it as well, I think would be good. And then we can look at putting the ACK on the bus when we see a valid frame coming in. How exciting. Is the next step to deal with putting this... Yeah, sorry, I wasn't very excited just now. I was very sarcastic. Yay, it's working. We've got all the data from the frame coming through. So that's very, very cool. All the way up to 7 bytes. And the scope decode is matching up with what we're seeing, which is awesome. So I think now we can do one of two things. We can either do the protocol decode and display on the Python side, or we could look at doing the CRC on the Glasgow and verifying it at that point. I also kind of feel like it might be neat to actually frame these packets going up to the Python, because at the moment it's just kind of a collection of bytes that get pushed over USB. And if, for example, we hit the invalid state, the illegal DLC value that we've put in there, then it will currently just sort of chop the packet off short, and then you'll be out of sync all of a sudden with everything else. Equally, if we get an invalid CRC, what do we want to do? Do we want to sort of keep the entire frame on the Glasgow until it's verified and then push it up? Or do you want to push it up as you go and then just say, oh, by the way, that message, that frame I just gave you is invalid. And I didn't acknowledge it, that kind of thing. Framing, yes, okay. That could be kind of interesting to look at. This is something that I know White Quark's been interested in doing for other stuff. And I remember the name of the scheme. It was called... I was thinking about it just earlier today. The scheme where you have a... No, I don't think so, at least. HDLC, what's that? No. It's a scheme where you get your bytes like this, and you put a so you put a number in instead of the 0 values. So if your data is 1, 2, 0, 3, 4, for example, to frame that, you would say it's 2, 1, 2, and then you'd say it's I think 3, and then 3, 4, and then 0. And this 0 gives you the synchronization point, and nowhere along the packet do you see the 0 apart from at this synchronization point. So to decode that, you see the first byte and you say, okay, I've got 2 bytes until there's a 0. And so you decode that, you go 1 byte, that's 1, 1, 2 bytes, that's 2, 2. And then here is a 0. I know that's a 0, so I'm going to put a 0, 0 in there. And the fact that it's not actually a 0 in the stream means that this is a continuation. So now there are 3 bytes before a 0. So you go, okay, 3, 3, 4, 4, and then we hit, so this is 1, 2, 3, this is a 0, and it's actually a 0 in the stream, and that means it's the end of the frame. You think your browser got a headache from this? I do apologize. This does require buffering, and you need a look ahead of at least 255 bytes worth. But I think that might be okay. And if we can implement it as sort of a similar kind of interface to a FIFO, then that could be quite neat. Unless, of course, the 255 bytes is too much. Unless I double the size of all messages. What do you mean by that? I can't remember what it was called now. That's really going to annoy me. I bet you it's in the not too distant history of the Glasgow channel. Let me just grab it quickly. Ah, here we go, COBS, of course. Okay, thank you for that. Cool. Oh, I see. Yes, okay, so COBS is consistent overhead byte stuffing, and this is the scheme I just described, and it allows you to have So the scheme that you're referring to, Omni, there, where you have a 0, 1 and then the byte until you finish, that's got a, oops, I just clicked on something. That's got a 50% bus utilization. Oh, sorry, get rid of that. Now I can't see my OBS because I'm clicking on all sorts of things. There we go. So yeah, so if you have a 0, let's get this back. If I was to encode this data using the scheme that you referred to just now, I'd go 0, 1, 1, 1. 0, 1, 2, 2, 0, 1, 3, 3, oh sorry, 0, 0, 0, 1, 3, 3, 0, 1, 4, 4. And then I guess 0, 0 to say end of frame. And so that's got a 50% utilization or a 100% overhead. Whereas the COBS, it introduces an overhead of 1 byte per null in your stream. And that's kind of neat. I like that. And this is something that I think Whitecork's been toying with for getting other kind of data out of Glasgow that needs framing. So it might be kind of cool to play with that now. Agreed, low latency, yeah, but at the same time, if we're dealing with CAN frames, then you take in the CAN frame and you know it's the end of it. Therefore, you need at most, I don't know, 8 plus the framing of CAN, which is 1, 2, 3, 4, 5 bytes of buffering. Maybe I don't know if you if we'd like to play with potentially doing some kind of COBS implementation, then we could do that. If people, what were the other options I outlined earlier? We wanted to do CRC on the FPGA. And we wanted to do frame decode in Python. I guess the frame decode is pretty straightforward, so that's probably an easy win. COBS is probably quite large, and CRC, I feel like I don't remember enough about how to do a CRC. They're kind of just shift registers though, aren't they? So I'm not sure why I'm scared. Like click. What? Like, lick. Redundancy check, thank you. Okay. The trouble with Wikipedia is it's also theoretical and magic. The X or Y, X or Z. No. Computation. To compute an n-bit binary CRC, line the bits representing the input in a row and position the n+1 bit pattern representing the CRC's divisor called a polynomial underneath the left end of the row. So that's a 4-bit polynomial with this mask, okay, and this is the input. Start of the message to be encoded. This is first padded with zeros corresponding to the length of n, the CRC. So that's padding, I think, and then let's run through it. So you take that, take your polynomial, and you XOR the values through, and then you shift it along one, and then all the values through. Okay, so actually, yes, this should be fairly straightforward. If we have a look at the CAN datasheet, polynomial is there. We've even got, look at that, we've even got a little bit of pseudocode in here. I think, yes, Omni, we're just doing. I don't know. This is all data science-y stuff, and I'm not so good at that side of things. CRCs and checksums and stuff and hashes are all a bit magic to me. The point being, though, we get shift register with zeros in it. The next is the next bit XOR the CRC RG, don't know what the RG is. Is that this? 15-bit shift register. Oh, that's the shift register, okay. 14. And then 14 to 1 is shifted to 13 through 0. And then RG 0 equals 0. And then if CRC next, so if that's a 1, then you take the whole shift register and XOR it with 4599 hex. Why 4599, I don't know. Not yet, at least. Is that this? Yeah, it is. Oh, thank you. This is just OBS. I can have a look, see at the filters if you'd like to have a look at that. Yeah, so I'm using the mic as the duck source, and these are the values. So we're ducking sort of slowly, hopefully not too harshly. That's all right. Happy to talk about it. And then the compressor as well is to maintain loudness, because I sometimes talk quietly or I go off to the scope or whatever. That's kind of a side point, but this ducker is the main thing. Yeah. So if you take a screenshot or whatever, have a look at the values, then I can move on. Hope that's okay. Tell me if you need it back. So I think then XOR 4599 I think is this polynomial. Hey Peter, what am I doing? Calculator. Oh, thank you. Right, so we have a 15, a 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8. I think that's correct. And if we then type that in here, we get 5C99, which is not 4599. Did I put an extra number in there? Is this actually a 15-bit value? No, because that's no longer 99, is it? 5C, what's 45? That's this. Have I got this wrong? I have got this wrong. What did I do there? That's 15, 14. So, for anyone who's just joined, including Peter, we are currently playing with the CAN stuff, and we're trying to look at putting the CRC calculation in the FPGA. And this is something that I've not done for a long time, and I've never done on an FPGA. So, oh, look at you with a website. Let's have a look. This could be good. Can I put in my own polynomial? So the interesting thing here is that we've got a specific polynomial and it's a 15-bit CRC, which makes for potentially an interesting situation where I don't think this will help us. Too short. I don't care, just show me all the things. I don't know if it has a name. Yeah, no worries. Quite cool calculator there. Thank you for the link. I shall try and remember that one. I think let's come back to this. So in here. Yeah, that's fair enough. Oh, has it frozen? I apologize. I'll wiggle some things around. That's just David. Try a refresh. So anyway, back to the CRC. Here is the polynomial, and I don't quite know why I got an extra one on the front, but maybe that's because of how this works out. But if we get rid of that extra one on the front, then we get the correct value, so 4599, and that's the polynomial. So it looks like what we need to do, if I rewrite their pseudocode because it's a bit grubby, initialize the value to 0, and then run through the bit stream. The next bit XOR the C bit 14. Okay. Nice, welcome back, David. You're referring to the extra one bit that I read out of the polynomial expression here. Omni. Yeah, I'm not too worried. Let's try something, see if it works, and if it doesn't work, we can come back and try and fix the value that we've read wrong or whatever it might be. Let's leave that notepad. I can get rid of this one. Get rid of this one. Okay. So the CRC, basically we shift the new bit in, So C equals so 14 down to 1 is the existing 13 down to 0. Yeah. And then cap that with the new bit. Yeah, correct. So this 4599 doesn't include the x power 15, which is unexpected by me. So this top one is the one that I wrote down while reading this, and the bottom one is the value of that XOR down here. So we shift the new bit in, and then if the next bit, if new bit XOR okay, we actually need to keep the old top, don't we? C14. That XOR O. We can optimize this a bit in a sec. Then C is equal to C XOR OX4599. And what we can actually do is C14 is that, else this is a very good point. I think the issue here is that what they're doing is they're shifting the new bit in, so it then becomes, you know, the most significant bit falls off the end, but then they're actually using that most significant bit to figure out whether they do this XOR or not. And I'm not convinced that that is in line with this, because it seems like there's an extra decision in there. So here, you just shift your polynomial along, XORing it with the value that's in the shift register each time. Whereas in the spec here, they're not doing that, I don't think, are they? They are taking the most significant bit and making a decision on that, whether or not you XOR in 4599 on each iteration. Otherwise, it's just a shift register. If the new bit XOR the top bit, which is about to disappear, is never a 1, you never XOR in the polynomial, or the 4599 hex. Anyway. So this becomes 13.0 new bit. Otherwise, C equals cat C13.0 new bit. I think that holds up. Would you agree? That follows what they're doing there? Yeah, I think I'm comfortable with that. I'm going to put this on the other screen. Let's try and implement this. It's going to be in, I think, a new module. This is indeed a cursed 15-bit CRC that I don't believe really sticks to CRC rules, but let's see what we get from what I just read from the datasheet. I might be wrong. I might be too simple. Yeah, Omni, it's weird, isn't it, I think? Never mind. Okay, this is the CAN low level, and this gives us a bit pulse. oh sorry, a strobe that we can then operate on. So let's do m sub modules.crc equals can CRC and give it the low level. I'm gonna give it a low RC. No, I'm not. Scope's gone, that's cool. You can see all the way down here, okay. We need an output, and that output is a 15-bit signal. Out equals signal 15. Elaborate self platform. When will I affiliate? Oh, Esden, that is something I've been pondering actually. If people think I should do it, then I might go for it. There seems to be a description of the algorithm here. Is this specifically CAN or is this generic CRC? Oh yeah, cool, okay. So I think instead of reading this, I'm gonna carry on with what I got and see if I can magic it up, if that's all right. In the earlier comments about the 16-bit polynomial for a 15-bit CRC, reviewing a simpler case for a 3-bit CRC in there, where the 3-bit CRC also takes a 4 bits in the polynomial. That is interesting. Thank you. Okay, I will see about it in that case. I've not been on, streaming so much in the last couple of weeks because of personal reasons, but I'd like to be, and I have in the past, so maybe I will get going on it. Right, don't want F12s in that. Here we are going to try and put in a CRC module. Oh, we need a reset as well, don't we? Reset signal. So that will allow us to sort of start again. Ugh. I can't do typing at the moment. If we're resetting, then make the C equals 0. So that's going to wipe it out. Otherwise, if we have low level dot, and I think it was called something like RX ready. So that is this strobe which tells us when we have a new byte, and that will also step over the stuffed bits as well. So that takes care of all of that for us. So here we need to implement the CRC stuff. Otherwise, we just sit and wait, sit tight. Now, so the low level has the bus, and the bus has the RX signal, which we should pluck out. So the new bit equals self LL bus RXI, just to keep hold of it. Then we can do with if this is the, so I'm referring to this bit that I wrote up earlier. I'm afraid it's, can I pop it in here? Yeah, let's put it in the top here. There we go, everyone else can see it now too. So what we're doing is if the new bit XOR with the C, we haven't got C yet, so let's make a C. Signal 15. That C actually I think is the same as out, is that right? Yes, I think it is. The RG is a 15-bit shift register, and that is the same as out. Okay, so we don't need a C. So if that is the same as self.out bit 14, then we have to do self.out equals, and this is with a md sync. Sorry, I'm pushing all the magic buttons tonight. md sync. Yeah, I did it again. There we go. Right, so we take a cat and we want to shove the new bit in the bottom. I did the cat backwards in my notes, but that's fine. Self.out 0 through 13. Like that. And then we want to XOR it with OX4599. Else. I feel like that's it. Yeah. Oh, did I miss something? Is there an update on the crowdsupply campaign? Oh, why don't we just have a quick look at that then? If nobody minds too much. Where do I go for updates? Case development. There we go. Let's look at the pictures for now. Very nice. Oh, we've got access to... Oh, that's fantastic. Yeah, okay, so since I last saw it, we've now got access to the LVDS header, which we didn't have before. Is there some options for the reset button we're looking at here? Oh, they're the old cases. Oh, first physical prototype. Oh, okay. Sorry, I presumed they were new at the top. The beginning, yes, gotcha. Apologies. Okay, down, down, down. All very good. That looks good, actually. I know that was a concern for quite a while, the LEDs bleeding. Nice one. Well done, Team 1. Back to work. Okay. Oh, I'm sorry for being one of those people. Okay. This is good. I'm going to close that, and I'm now going to push the CRC we've calculated up. And I'm going to do that. So first of all, we need to reset this module. MD combinational null crc.reset equals fsm.ongoing idle. So it will reset all the time while it's idle.
It will be your friend, no more than the table you built it on will be.
And then what we're going to do... Yeah, it's interesting, isn't it, about the order of events in terms of showing things to people. People come to updates like that for the new stuff. And when you... I just did it immediately, and I apologize for doing it, but when you sort of feed them with the old stuff first, I think the first thing people see go, ooh, and because I've not seen this render before, I immediately went, oh, hang on, this means we can just pop in the RAM pack and things. That would be very cool. So yeah, it's very interesting. In terms of these, I didn't read, so apologies if I got it wrong, but the the clear pipe, I think, does the trick in terms of, yes, obviously the frosted pipe looks nice, but the LEDs bleed very quickly between each other. The clear pipe, you obviously get the internal reflections and stuff, which is potentially awkward. If you're at an angle, you get sort of the parallax effect type thing going on, even worse than otherwise. Anyway, enough of that. What are we doing? We've reset the CRC module. Now we need to actually then take the value it's got and feed it to the computer. I think before the idle wait, we are going to also now feed 2 bytes. CRC1. I'm going to do this lazily. CRC2. And in here, we're just going to pop this. That is then going to be crc.out, and it's going to be bits what? The first 8, so that we want the high. Oh, I'm so confused already. So this one, the second one, is going to be the low bytes, the low byte singular, sorry. So that's going to be :8. And this one is then going to be 8 colon, and I think that will take care of it, apart from we actually now need to concatenate that with some padding. I think at least. Signal is, no, const 0 unsigned 1. Look at that. Is that going to work? Maybe the pictures should have giant semi-transparent redacted or deprecated, yeah. LEDs and calibration is a fascinating topic. I'm sure you're all aware, but human eyes are not nearly linear, and for various different wavelengths and different pulses and all this sort of thing, they respond very unintuitively. So a green, for example, our eyes are much more sensitive to green than the other colours. But the issue now is that if you get an RGB like lux meter or light level sensor, you can't just point at an LED and then point at another LED, because actually A, our eyes don't respond the same way as these meters, but B, the meter has its own response curves which sometimes try to mimic our eyes but don't necessarily do a great job of it. White meters certainly are not flat. There's a massive hump in the middle. It's amazing. I love biology and all this stuff. Yeah, it's not me that's wrong, it's everyone else's eyes that are wrong. Oh, sorry, all the instruments that are wrong. Oh, that's neat. My friend actually plucked an old ISA card spectrometer a little while ago out of eBay, and then they got an old computer and all of the bits to make it work, and very jealous when I saw that. Oh yes. Is it going to work now? What's also amazing is not just how human eyes detect colour, but how other eyes detect colour as well. So here we are, 75 AF, and the CRC we calculated was OE95! Brilliant. Okay. That was not planned. So just to confirm, can't see. There we go. So the CRC is 75AF, which is what we are pulling up off the line. But unfortunately, what am I doing? Unfortunately, that's not what we have calculated. Oh, I got a, I wonder if it's still on my shelf. Yeah, I got one of these chappies. Which is I don't remember. It's got a pen marker on it, and 9960, something or other. And this has built into it 4 light sensors, one with no filter, one with red, one with green, one with blue. And it can do RGB white or RGB clear light level sensing, but it can also do sort of gesture, so you can move your hand in front of it. And because of how the sensors are placed, it can actually determine that your hand was going left to right, for example. That kind of neat stuff. And the Glasgow REPL interface just makes interfacing with that just so easy. It's crazy. So can the bit stuffing affect the CRC? Yes, and you're not supposed to CRC the stuff bits. I agree with that, and I don't think I am CRCing the stuff bits. The thing that I am doing, which I probably should not be doing, however, is CRCing the CRC. Let me just check that. So in here we get which are given the destuffed bit stream consisting of starter frame, so that's a 0, I think possibly that I'm already not CRCing, arbitration field, control field, data field if present, and for the lowest 15 coefficients by 0. What does that mean? This polynomial is divided. Coefficients are calculated mod 2 by the generator polynomial. Oh, is amazing. What I love as well, there's a nerve which runs down. In humans, it's not so bad, but it runs, I think, from the brain sort of down and round something, and then back up to the brain again or something. I can't quite remember where it goes. But the fascinating thing, right, is that same nerve exists in giraffes, and it runs all the way down their neck, round a bone, and then all the way back up their neck. It's like, what? How did that happen? I'm sorry, getting too excited about giraffes. It's amazing. Oh, fascinating field. Sorry. Yes. Okay. Back to topic. So starter frame. I think I'm not CRCing that. Okay. This means I probably need to go into. I need to CRC it immediately on the RX trigger, which means that the reset here needs to be. What is the RX trigger? Let's have a look. See, that's the inverse of the bus input. Let us put the CRC reset signal on the debug pin, I think. I think that would be a good idea. Sorry, I'm not reading chat. Yeah, exactly. Yeah, you can't disconnect a nerve and move it the other side of a bone or whatever. So yeah. You mentioned CRCing the CRC. What value is it initialized to? The CRC should be, and I think is, initialized to 0, so that's handled here. and CRCing the CRC. So if we have a look at the framing here, we are supposed to CRC the starter frame, all of this up to the end of the data, but we're not supposed to run CRC over this or any of that. So the CRC has to finish at the end of the data and include the starter frame. And I believe that the CRC you generate over this portion here should match that. There are other checksum algorithms or schemas or whatever where you run your algorithm over the entire frame and it should equal 0, for example, or FF, or whatever it might be. Peter, don't come at me with a bit of logic and reason like that. I typed in nmygen CRC and nothing came up, so I'm going to leave it at that. I think, to be honest, the main thing right now is not the implementation, because I think we've got that here. I think the issue is our choice of what we are CRCing. So I've put the reset line on the scope. Let's rerun Glasgow, put this onto the correct pin, and see what the scope says. There we go. Now this should be high. Oh dear. Not what we wanted at all, is it? That is... yes, okay, I know exactly what's going on. That is going on for the duration of the wait idle. There you go. It goes low way too late, so it's including everything in that. We need it to stop. So, I don't mean to tell you to shut up, of course. But, yeah. We need it to stop running when we reach the end of the data. Exactly. So I'm going to do self run signal. Now, I don't want to reset, but I do want to gate the running of it. So while self.run and that, we can do this. And self.run, CRC run equals FSM ongoing. We need to, let's just make a new signal. CRC, no, we don't need to do that. In here we can do md sync crc.run equals 1. And then as soon as we get through the end of the data and into here, we do crc run equals 0. Then we should change this because that's the reset. Excuse me, and that's not what we're looking at anymore. We're looking at the run signal. What do we think? Chances this is going to work? Well, if we look at the scope, we have something that looks a lot better. But it's still giving us the wrong value. We expect a 75AF and we get 592A. Now then. I'm still unsure about the first bit. Zoom in on that. Well, it's probably okay. Yeah. If I CRC'd the start frame, but that's the one I'm currently trying to figure out. I suspect. Okay, so Rx trigger is the inverse of the Rx input. And the input is idles at, what is it idle at? 1 or 0? I can't quite remember this one. Where are we going? RX trigger is the inverse of the input. Get rid of the scope. Keep that handy. The RXI then is the CAD. Never remember. Glasgow CAN. Look at this one. One of them. Texas Instruments, CAN 1051 Q1. So the RX value is low for dominant, high for recessive. So this output is the same as CAN low. Okay. That means that the RX trigger is the same as CAN high, kind of ish, or it's the inverse of CAN low at least. So as soon as that goes low, we hit the trigger. Pop. That trigger is then what starts the counter in here. So if we're idle, we get the trigger and we start the counter, that then enters bit phase 1, etc. So I do believe that, yes, this is actually a 10 plus 1. And that one is for start frame. So I'm pretty confident now that, yes, we are including the starter frame in the CRC. Where do you put the bits in the CRC? I put the bits into the CRC in the CAN CRC module here. And this is what I just wrote after reading the datasheet and taking some notes just now. So on the reset, we set it to 0. So that's this bit here, CRC register 0. Otherwise, if we are running and the RX ready pulse is coming in, the stuffed bits are handled by the low level module here. So we have the RX ready and the RX ready raw. Might be worth commenting these. RX ready. Okay, let's start with RX ready raw. That is asserted always. I think. Bit phase 1. Yeah, so at the end of bit phase 1, that is asserted. So that equates to here. So that pulse wiggles does its thing. And you then move on to bit phase 2. And finally, we get bit phase 3, which is technically not something that is named, but that's just to deal with some nasty brain farts the other day. So that's RX ready raw. We then have RX ready. So RX ready raw happens on every single bit period. RX ready raw happens on every single bit period. RX ready, on the other hand, happens, here we go, only if we have no bit stuff. Like that. So the stable counter is saying how many bits were the same in a row, and once you reach 5, this is now a stuffed bit. Okay. I think I'd like to clean up this module, but I won't do it on stream, I think. So this is strobe for bit RX bits, and this is a strobe for all RX bits including stuff. Right, so we're using the RX ready. In here, paired with the run flag that we've just given it, to say the algorithm should run. I think that's okay. And then in here, we're saying the new bit is the bus RXI. So that is the new incoming bit. I think that's okay. I don't think it needs inversion or anything. And we're then concatenating the new bit onto into the shift register. Now this could well be a point that I am falling down on. Let's have a look at the RX data here. Okay, let's swap out that 13 for a -1 because that makes a lot more sense. And actually I think 13 was wrong because it probably should have been 14. Yes, it almost certainly should have been. Let's just run that because I think that might stand a chance of getting things right. This is the same as we were seeing before. Pop. And we see 75AF is the checksum, and now we're doing 57.4. Okay, so it's still no good. Now we're doing if the new bit of 14, I'm going to put a -1 in there. New bit XOR that. New bit XOR that. Should have been using 15. Yeah, that's... So here they're using 14 because they're doing 0 through 14 for a 15-bit field. Here I have a 15-bit field and I'm using -1 now. I was using, what was I using? 14, which I think stands up, but let's put -1 because that will take the most significant bit, right? -1, yes. $4599. Do I need to? I think that should be okay. Not inside a const, but I'm going to put it in a const. Unsigned 15, just to see. Because it's doing a shift register. That's why the :-1. So we're taking all but the most significant bit. And that then gets put into out here. That didn't rebuild the gateware, so that kind of implies it's not going to make any difference. Doesn't want to, does it? Run, I think help goes in here to figure it out. Rebuild. I don't think that'll help, but why are you not keeping the most significant bit to do your XOR with? 1 second. Yeah, okay. Why am I not keeping the most significant bit? The most significant bit is used here to do the XOR. And so in their algorithm here, we've got the new bit, XOR the most significant bit, is put into CRC next. Then they do the shift register bit. Oh, they put a 0 in there. Ah, I'm not putting a 0 in there. I'm putting the new bit in there. Let's put a const 0 unsigned 1 in there. That is a big mistake. There we go, look at that. 75AF, 75AF. Woohoo! Oh, that's exciting. Try and get excited at you, come on. Do you reckon that's exciting enough to have a biscuit? I need the original 15th bit. Just one biscuit, yeah. I'll stand up and get it in a second if Omni will let me go. So the pseudocode here, yes, they take the most significant bit and they XOR it with the next bit, the new incoming bit. And then that's basically put into a variable because after that, this is procedural, don't forget, this is not FPGA land. So they keep that, next bit XOR that, and then they do the shift register and they put a 0 in the bottom, which is where I was putting the new bit in instead of a 0. And then after they've done the shift register thing, they then test that XOR they did previously, and if it's true, they then XOR it with the 4599 hex. So here, putting that const in was the fix, I think, and it now seems to work. So we can put a few bits of data through. Did I see the link earlier? I don't think I did, apologies. Let me scroll back. If you have it again, feel free to send. Oh, this one. On the Wikipedia. Yeah. The question remains, why not just do the whole shift register in the cat and let it truncate? Okay, the cat here is used purely to simplify the code a bit, and it's then going directly into self.out. So if that was, for example, a 16-bit value trying to go into a 15-bit signal, correct, yeah, I haven't updated it yet. I'm just using it for sort of clarity, I guess. Although I'm not making it clear because obviously you tripped up on it. Yeah, so that just avoids duplication. And it's the new bit used here with XOR of the most significant bit, which is still the same. It hasn't been updated yet. Oh, does it? Okay, I did not know that. Let's give it a go. Get rid of that, see what happens. I feel a little bit weird doing that. Yeah, I agree, a little bit mad about that. I don't like silent truncation. Yeah, that does work. I feel like I don't want to do that. I'd keep it. Hopefully it's clear and you're sort of following the process now. I'm going to go and get myself a biscuit. Wee biscuits! Look at that! Digestives are, by the way, by far the best kind of biscuit, if anyone's asking. Code fragment for shift register. If the chewing is problematic, tell me and I'll mute. I think you're right, it is quite similar, isn't it? Anyway, we got it working, so that's cool. Thank you, everybody. Let's put a few bits through. That's 674C, that's correct. This is looking good. Oops. Oh, I've gone off the end. Yeah, cool. Yeah, I think you're quite right. Obviously we're in an FPGA, so it makes it easier to do things bitwise instead of bytewise, but cool. Okay. Happy. So that's the CRC done. That was not nearly as painful as I was anticipating. Wasn't showing my screen, sorry. Okay. That's good. We have done the CRC on the FPGA. We now need to actually make use of it. So let us perhaps yeah, rather than actually transferring the CRC to the computer, let's just transfer a good or bad, perhaps. What happens if I put the CRC bits into the CRC? Let's try it. I am curious about that too, actually. So I've just moved the run flag, setting it to 0 after the CRC has done its thing. And that should be good. In the scope pack. So that blue line should now extend over the top of the CRC as well. Boop. Oh, it does go to 0, 0. I like it. Yeah. It is stable by the looks of it, at least with our limited test data. Yeah, nice, cool. I wasn't aware if it was a generic property of all CRCs or if it was sort of certain polynomials or whatever we'd give it to. So yeah, that's cool. We can indeed check for zeros. Right, so instead of sending any of this to the host, I'm just going to say that there was a good CRC or a bad CRC to the host. If it counts to 0, then we can just send. Let's do a CRC.out equals 0. And then we'll need to corrupt it somehow, I think, as well, won't we? Actually, I'm going to put that back just for now. So this should always give us a 1 or a true or whatever that comes out to. Yeah, that's very true, isn't it? You speak logic. Put this here. What was it we had? CRC.out equals 0. CRC3. This is icky, but we can fix it later. Okay, here we go. We don't need the other two states actually because we're confirming it already, but we can prop them up in a minute. Okay. Oh, a 1. A 1. Look at that. Good stuff. Okay. I think that we are giving that as a trailer after the legitimate CRC. We don't then need any of this. Okay, so the payload that is going up to the host is the full frame followed by a byte indicating if the CRC was good or not. We can now, what can we do? In our little thing, we can do an ACK. Let's do an ACK, and then I can detach my other thing from the system. the network. There's a delimiter of one bit time, and then there's an acknowledge slot. And that acknowledge slot is where we have to drive the bus. Drive the bus dominant to indicate that we have successfully received it. So we need to wait for 1 bit and then indicate that. CRC, let's do... What are we going to do? CRC, let's just call it CRC delim. Oop. Now this is interesting because we have to transmit for the duration of the bit time, but we get a signal when we are good to receive. So here we advance state to the ACK state. Now when we enter this state, we are still in the tail end of the previous bit time. So if we have a look at here, we're still in this period here. So what we need to do is wait for that period to complete, and then on the end of the bit time, we need to then assert ourselves on the bus, wait for the full duration, and then deassert ourselves on the bus. And I don't think we have those timing information or timing signals coming out. We do not. Look. So what am I going to call it? Bit boundary. I don't really want to call it that, but I'm going to go for it for now. And that bit boundary will be pulsed when? I think at the beginning of bit phase 1. No, not at the beginning of bit phase 1. It needs to be at the end of bit phase 3. No, because that would then miss the first. So this is an interesting problem. We want a pulse on the fence posts. This pulse, this pulse we can generate with the trigger pulse signal, which is here somewhere, RX trigger. But only when we're in the idle state. And then, so that's the very first fence post. And then all of the other fence posts can be at the end of the bit time. Yeah, that works. That puts it at the end of bit phase 3.
Yeah.
Okay. The idle, here it is. If we get a trigger, yeah, we can just pop that there. Okay. So here we go with m.if ll.bit boundary. We need to then use the bus now. And we can go self.bus.t PX, I think it is. PXO equals, and what are we doing here? We are doing a dominant state to indicate that everything is okay. And a dominant state is a 0, and that then indicates that the little thingy here is crc.out is not 0. Should be good for that. So that gives us the start. This needs a lot of tidying up. We've got far too many states in here. And we're then going to go recessive, which is a logic 1. I think. TXO. Yeah, logic 1. Okay. And we're then going to skip on to CRC1. Okay. Is that good? The test here will be to disconnect the other board. Oops, can't do something about buses. Oh, not self.bus, it's just bus. ACK is referenced. ACK begin. Well, that looks okay. Shall I disconnect the other bus? We'll lose our scope, but you're not watching that anyway, so that's fine. I'm nervous. I think I want to keep the scope. I can put the other system into... I can turn off its CAN bus, let's do that. I'm not actually no, because that probably still acknowledge it, won't it? It's handled at a different layer in the system. It's handled by an STM32, not by Linux. Yeah, let's just disconnect it. And we should be able to, oops, okay. Oh no, it didn't happen correctly. That's annoying. So this is the issue with this sort of half-written firmware, is that it will just keep sending the message over and over again if nobody acknowledges it. So if I connect the other system to hopefully acknowledge it now, it will hopefully stop. But this does mean that we are not acknowledging it. Okay. Somebody else is acknowledging it. It has to be sure, yeah. I mean, there are technically some quite strict rules about how to deal with backoffs, and if nobody acknowledges your message, you should not do that, basically, on CAN bus. But never mind. Okay, how do we know? I wonder if just inverting this is going to do the trick. I don't think it would though, because we are trying to do a dominant bus state in the acknowledge slot. Let us, let's put the debug signal in there. Debug SPTO equals, put that high, put that low. Okay, this should identify on the scope where the acknowledge bit should fit. Nope, nothing there. Okay. Nothing at all. Nothing at all. Let's make it equal to the bit boundary. And that is l.bit boundary. We should get a pulse on the boundaries now. Oh, we do get lots of pulses. That looks, I think, reasonably good. Let's zoom in a bit. What are we going for? 8 microseconds per division to give us. Yeah, 2 per graticule thing. That looks good. The boundary is high for a lot longer than I'd expected, actually.
Don't be afraid to borrow.
Oh, it's high for the whole second part of the bit time, isn't it?
Little ditties, tiny things. Just snatch them all up.
I want to put that in here. I think that'll probably do what I was expecting. Yeah, that's better. Okay. Now if we scoot that around, we should get that to line up nicely.
I don't have a problem.
Yeah, it does. Look at that. Perfect.
Or borrowing something that I heard.
Okay. Go all the way to the end. Oh, need to do it again. Another capture. Thing.
And I used to. I thought it was not original, not creative. But
and I think that'll be the act there, won't it?
Or creative. I can't make up a new thing.
Tell you what, let's zoom out. Get the whole frame in, shot, and then zoom in like this.
And I very much doubt, anyways, that any of the people that I listen to were the first ones to think of a particular progression. And so once you get over that, sounding good is easy.
Okay.
You just borrow. Basically, let's just copy.
So that dominant state on the right hand side there should be the acknowledge.
No one will know.
And if I disconnect the other system, I think we'll get no acknowledge there.
No one knows.
In fact, we're not even triggering on the message. Oh, have we lost termination or something silly like that? No.
It's kind of controversial.
Is it?
Obviously, chords and
Are we triggering?
these
No, we're not triggering.
different things you can do.
Yeah, you don't want to push it. Don't be blatant about it. Be subtle. Like a sneaky thief in the night.
Termination on the Glasgow.
Like a little note.
Oh, that's actually a very interesting point.
For what you've done.
I think I was using that. Do you remember when the LED wasn't working? Or possibly during the bring up, I was using that for bad reasons, wasn't I? Let's remove that from there, put termination. So termination, there is a resistor in the, you probably can't quite see it, in the doodads here. What they call the little spring features. So it should be terminated. I can add termination as well. I think though that because we were setting it, we were enabling termination just here. That's not what we want to do actually. And what we do want to do is probably reset that to a 1 to just enable termination on the Glasgow at all times. See if that helps. What's the other system? That's got no termination. That's another STM32. It's basically the same as one of these. So this one's transmitting, and then there's basically a duplicate of it, off shot, out of shot, which is acknowledging it. Okay. The termination LED now is on, which is, I think, good. Signal's looking nice and square on the scope. Let me just bring you back to here. That. Yeah, still no acknowledgement. Oh, the scope's not triggering because the scope's not connected anymore. Okay, I'll tell you what. Why don't I rewire this quickly so that we can disconnect the other end. Yeah, exactly. Previously, when we've been working on this, I have connected the scope on the Glasgow end, but today, in my infinite wisdom, I connected the scope on the other board end. Here we go, bring the probes through. Okie dokie. So, I will disconnect that and put it on the this one. I don't know, it might be wrong. Can't remember how the scope's configured now. And I'll put the low on that probe. There we go. Okay, I think those are backwards. Let's swap them. There we go. Okay. Oh! Can't remember what we're looking for now. Right. Okay. That is a good frame. There's the acknowledgement there. So it's in the third from the right, graticule, division, whatever you want to call it. And it floats around a little bit because timing between systems and all that. Now, if I disconnect the other system, that goes away. Like this. Whoop, gone. And we get millions of messages over and over again. The ACK begin. I don't think we want equals 0, but I'm just going to try it, because you never know. Oh. Not sure if you can see that, but far outside the zoom window, between the frames, there's what looks like it might be an ACK. If I just connect up the other system again, like that, it just shaped quite a lot, doesn't it? And I think that's us being naughty. Rogue hacking, yeah. Miles out of spec. Way too late, etc. Yeah, okay. That is naughty, naughty, naughty. This implies then that this is way out of time. The blue currently indicates the bit boundary. Let's make the blue indicate the ACK begin and or ACK end state, I think. Let's do that. I do have 4 scope leads, yeah. You want another one? We can, yep. Should I do that? Just grab some bits. What's the other signal you're looking for here? Actually. Bit boundary and something to check when it's trying to act. Yeah, I agree. That would be good to see, wouldn't it? On, where are we going to put that then? Get rid of this. Put it here. This is the red one. Ow! Okay. Look. Wink. That is currently indicating the control field, I think. Debug. Debug. There it is. No, that's not what I'm looking for. Here it is. No, that's not it. Debug arb. There it is. There we go. Arbitration ID. Okay. So let's first identify the time period. Self pads debug arb to equals fsm.ongoing, and we're going to call it ac end. I think we'll do what we want. No happy. Okie dokie. Oop. Oh, that looks right. Oh, hang on. Let us rework this. I don't want to use sync. I want to use combinational. Because then it's temporary. Okay. Oh, look at that. Scoot it off way to the right. That's correct. That's not correct. That's correct. That's not correct. Interesting. What's going on there? Oh, and look, the data we're getting to the PC is all wonky as well. That's correct. And that's not correct. So this is a framing issue that we were seeing earlier, but I thought resolved itself. Is this all to do with zero length packets or zero data? If I just do 0, 0, for example, let's zoom out a little bit. That's gone off the end, and that's correct. And that's gone off the end, and that's correct. Hmm. 6502. Exciting. Rebuilding from the beginning. Okay, so this red should now indicate the what should it indicate? The CRC field. The spike on the green, I think, is almost certainly the crosstalk from the red, if that makes sense. And there's stuff. Very good. Yeah, okay, so this is a problem because that CRC field should not be moving around like this. How far back do you reckon this goes? Do you reckon the data is also wonky? And why? I thought it was all okay just now. So this should now indicate the data field. Oh look, sometimes it's 1, sometimes it's 2 bytes. Is that? If I give 0 bytes, well, that's not 0, is it? There we go, that's 0. That's not 0. What? What's the state before? ARB control. Arbitration control. Boop. No, it's 1 bit shifted, look. 1 bit shifted. Okay, that's annoying. And it goes all the way to the top. So this should now be the ID field. Yeah, look, the ID field gets 1 bit longer periodically. Why? Is this some synchronous counting type issue? Yeah, exactly. How does it get 1 bit longer every now and then? And it's alternating as well. It's 100% every other time. That's no good at all. Before that, we have the idle. I don't think this is, I think this is, I'm tempted to say that I think this is going to be correct and that this indicating the idle state is going to be accurate, but I also have a feeling it might shift 1 bit back and forward. No. Okay, that is accurate. That indicates the idle state. So then, we're going to need to figure out what's going on with the arbitration ID field, because that's knocking everything else out. So if we put one of these channels, the blue one is now going to indicate the RX ready point. So that's the sample point of the bit. And the red is going to continue indicating the arbitration ID field. Yeah, look. That's a little bit difficult to see. Oh, and you're not even watching the scope, apologies. But look, we do periodically miss. Look, what's going on? We miss that first pulse every other time. There it is. And now it's gone. And it's back. And it's gone. And it's back. So that's why it's a bit longer and shorter. Ooh, indeed. Okay. This is to do with the low level module. And excuse me. The low level module takes care of this stuff. What we want to get there is a sink that is alternately inverted and causes this trouble. So I want to avoid the alternately issue. That is quite a lot of noise, I agree, but I don't think it should be the cause of our problem. Boop, gone, boop, back. Yeah, I think I agree with that. It's almost like I need to reset the state machine in the low level stuff when we are returning to idle. Wouldn't you say? To be honest, Keystorm, the part of the issue here, I suspect, is that my probing is awful, and I've got a nice long and one ground line for all of the signals and that kind of thing. So what you're seeing on the scope is probably actually not super representative of what is going on sort of in the system, if that makes sense. I'm just being lazy. So don't read. I don't think there's any need to read too much into the noise there. So in this case, I want to look up how to do nmygen fsm reset. Yeah. I want to return the state machine to a known state on external influences. I suspect it might not have a reset as well. I suppose suppose winding back, why was this okay previously? It seemed quite stable. And now, for some reason, it's not stable anymore. I could just sort of sit on the U key for a little while, couldn't I? Undo. Get rid of all of the acknowledgement stuff. Oh, do you reckon that could be part of the problem? Yeah, let's try that. Does it depend on bit length? No, you can send a static packet every single time and it just alternates back and forwards. Yeah, so it's still doing it. Let's keep undoing. Undo. I'm going to leave it at this state. I think that was good, if I remember correctly. I think when we saw it like an hour or so ago, it was unstable with the 0 length data. There we go. Yeah, so that's stable now. But yeah, so we resolved that issue. Okay, so this is good. This is good, known good. Copy init to good. Hi. Peter, am I not showing the mic? Oh, the oscilloscope. Is that what you're referring to? Yeah, we're just talking more about code and stuff, and it gets in the way, unfortunately, so I turn it off and on. So if we redo all the way to the end, that should then be in the unstable state. So here, yeah, now it's unstable. Okay. Copy bad. I should have been committing a lot along the way, and then I could just do a nice bisect or something, couldn't I? So annoying. Let's just diff the two, see what we get. Good to init bad. Probably quite a lot. Oh, the termination's been turned on. We've added the bit boundary signal. We've changed the debug. We've added in the CRC delimiter and then the attempt to acknowledge the CRC. Do you reckon that could be it? Just do some commits now, yeah. Not a bad idea, actually. Init.py, init is now.py, and then we can copy init good to init. Good. Bad. Now to init, and I think there's no difference there. Yeah. Okay, so the difference is that we are trying to acknowledge that we've added the bit boundary signal and that we've turned on termination. So let's do those things one at a time. Termination, bit boundary, and back. Termination off. That would be weird if turning termination on caused this issue. Let's bring the scope back. Boop. No, okay, so it's not that. Still bad. Next, we wanted to try the bit boundary. You just adjust the CRC delim state. I think I will remove the. Not here, sorry. Where is it? Here it is. Here's the CRC delim state, followed by the ACK begin, ACK end, and the CRC one. So I'm going to snip that out and see if that resolves it. That's the big one, isn't it? And that's the end of the message as well. Yeah, there it is. Stable. Excuse me. Okay, so what on earth did we do in there? Hang on. What have I done? Here we go. That's what I want. Okay, so from the CRC state, we go into the CRC delim state. From there, we go to the ACK begin state. Hang on. Get the diagram up. Might skip this song. Hope that's okay with everyone. Bit exciting, isn't it? Yeah. Okay. The CRC. We then go into the delimiter. So when that equals 0, we've got everything we need. Move on to the delimiter. The delimiter, then we on Rx ready, so that's halfway through the CRC delim. Yeah, I was wondering something like that. So halfway through here, we advance into the ACK begin state. And that doesn't then actually push on to the ACK end until we see the bit boundary, which is this edge on the left. And then, sorry if I'm hiding it, and then that will wait for the ACK end, which is there, at which point we will, ooh, look, that should not be there, that should be there. And when you advance out, I don't see how that would help though. What, where? No, that doesn't help. This, the acknowledge, driving the acknowledge onto the bus was inside the if, which would mean that it doesn't do it until the far end of the bit boundary, and then even then it only does it for a single clock cycle. Eagle code, yeah. We are using the scope and a couple of signals, the blue and red signals, to identify or to try and sort of mark events and things that are happening in the system. Oh, hang on. We are turning the CRC off there, not there. I don't see why that would affect this as well. Why does it happen in the ACK end state? No, that's not it. It's not really end so much as wait for end. Bad naming. Wait for begin. So we advance into the ACK wait for begin state on the sample point of the CRC delimiter. And then on the bit boundary, we advance into the ACK wait for end state. So that covers the entire ACK bit time. during which time we want to output and acknowledge if we got the correct CRC. And then when we get the end of that bit time, we want to advance onto the CRC1 state. I'm going to snip that out. Can you, oh, sorry, what are you saying? So, can you get the state signal for an FSM? Yeah, yeah. Oh, look, it's stable. Yes, we can get the state of the state machine, and I've been using that up here to output to the debug signals. So FSM.ongoing, for example. So while we're in the arbitration ID state, it will assert the signal. I'm going to cut out this one. Squeaky chair, sorry. TikTok. 555, 555. Okay. Well, that's very interesting. I don't understand what's going on here. That's now stable, look. By removing these lines here. I don't believe that commenting out that will have this effect. I just snipped out these lines so that the ACK wait for end state just immediately advances to CRC1. No, it doesn't. So the fact that we're waiting for the bit boundary in here knocks everything else off. Let's put that on this pin then. ACK wait for end. That's exactly what I'm hoping to see now. We will have the, I don't remember which, one of the signals. There we go, the red signal. High. There, look. Oh, you can't see. So the red signal there is indicating the ACK wait for end state. And it shifts. Oh, no, because this is all interdependent, isn't it? The very first time it runs, everything lines up okay. The next, and that looks okay as well. That covers the what looks like the ACK. The next time you run it, the first pulse, the first RX ready pulse, doesn't occur until 1 bit time later, and everything else then gets shifted out. But the point is that this bit boundary signal is seemingly advancing it from this state correctly, isn't it? Is it possible state machine doesn't go back to the start state? We did put the idle state on that signal, so let's just do that again quickly to test it out. Yeah, so I'll do the idle first, and then I'll come back and do the wait for begin. So the first one we can kind of trust. And there you go, the idle is deasserted at the very beginning of that bit time on the front. And the next time round, it's deasserted in the correct place, but the RX ready signal isn't strobed. Oh dear me. Wait for begin. got all of these stacking up now. So this is now going to signal the wait for begin state. Idle is supposed to be asserted after 128 bit times after the end of the frame, just because we were being lazy earlier. That then is correct, and that then is incorrect. We can't see that in the scope. Yeah, it's off the end, yeah. So if I was to put idle back on and reduce this to, say, 4 bit times instead of 128. So this will now indicate idle again. Yeah, it does return to the idle state, which is good. So there's that, and there you go, it's returned to idle. Oh, you can't see, sorry. There you go, return to idle. And then the next time, oop, everything is shifted. I think I want to, what do I want to do? I think I want to have some way of seeing the bus go idle for a number of bit times and just resetting lots of things. Lots of things, including the low-level module. Does some counter get left somewhere? I don't know. This is really bothering me now. I'm going to put that to 8 just because it seems to fit on the screen nicely. And 8's a round number. CRC1 will push the validity of the CRC as calculated on the FPGA to the PC. That will just run through those states. Let's have a look at the low-level module again. There's the bus, it doesn't do anything, it just connects signals. There's the low-level module. And it will count. It will count using its clock up to this point, which is on the diagram, it's here. Then, when it reaches that point, it will keep track of the incoming data. It will say if the last value is not the same as the incoming, then it restarts the stable counter. Which phase of the following frame takes too long? The issue is that the following frame is everything, all the sample points are shifted off by 1 bit, which means that the if we have a look at this, the arbitration field is shifted off by 1 bit, so therefore the DLC is shifted off by 1 bit, and its value gets multiplied by 2, and then obviously the data and everything else just piles on, and it just gets worse and worse and worse. And I can't see why, looking at the scope, if we run that a number of times, you see just under the arrow, the orange arrow, on the first bit, you get that blue pulse coming and going. And that's what causes the 1 bit shift, and everything else just piles on after that. Right, hey, wait. So stable count is equal to 0, so it resets. If the stable count is greater than or equal to 5, Error, this should be a stuff bit, but it wasn't. Naughty, naughty, make this blow up. Reset it to 0. Otherwise, stable count is incremented by 1. That all looks okay. If the stable count is less than 4, then shift the data in and go to bit phase 2. Otherwise, go to bit phase 3, and the RX ready raw is always pulsed. Bit phase 2 will pulse the RX ready signal, and bit phase 3 will then deal with counting up to the end of the bit time, up to here. Once it's reached that point, bit boundary is pulsed. Now this is the interesting bit. If we are no longer being told to run, then we return to idle and we wait for the next trigger, and the trigger is a bus going dominant. Otherwise, if we are still being asked to run, we reset the counter and return to bit phase 1. Now I wonder if this RX run is being handled correctly, perhaps. The blue pulse is derived from this, so that is the RX ready signal here. And it indicates the sample point for valid bits, not including stuffed bits, I think. That's an interesting point. RX stable count when returning to idle. Oh, what have you found? Omni fixed it! Look! Oh, sorry. You fixed it! Well spotted, thank you. Yeah, that's working well now. Happy. Cool. Yes, good, very good spot, thank you. Yes, exactly. Exactly that. Dope. Good job. What else have we changed? Lots of stuff. Let's revert this. I want to not revert that. I want to not revert that. Okay. Probably had troubles if you had a different ID too. I don't know. Why was it gobbling up the starter frame? Oh, it was seeing the starter frame as a stuff bit. And therefore, yeah, because a frame always ends with lots of recessive states. Here, you have the end of frame, which is an illegal state because there are so many recessive bits in a row, and then you got the interframe separation, which is all recessive as well. So all of these pile in together, and you see 1, 2, 3, 4, 5. So that would have been one recessive bit there. Oops, here, there, and then 1, 2, 3, 4, 5, and then we stop. And then this would have been seen as a stuffed bit, and then on it goes, kind of thing. Oh, sorry. Yeah, so I was talking about here at the end. So these end of frame bits here are technically in a legal state because there are so many recessive states all in a row. And then you got the interframe gap separator, whatever you want to call it, which is extra sort of padding effectively. And then it wraps around to the front starter frame, and all of a sudden the low level decoder gets turned on again, and the first thing it sees, it goes, oh, that's a stuff bit, I'll ignore it. And then it goes on. So yeah, cool, good spot, Omni, thank you. Now that we've done that, so we've got this running, we've got a valid checksum coming out. I think the end of frame, you're quite right, shouldn't explode. At the moment, not sure if you can see it on the scope. We've got a couple of pulses coming through before it then turns off. And it is actually seeing a, what's it called, a stuffed bit in there. If we scroll through, I think, yeah, there's a stuffed bit, look. You got two bits at the end, and then before that you got a stuffed bit. It's supposed to be lined up with that graticle there. So yeah, cool. Coming along. What can we send? One, two, three, four, five, six, seven, eight. Oop. Very cool. And that is also coming out in the computer too. So what we have here is the 55 is the address, or the ID, sorry. 3 is the length of the data, and then we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we have the CRC, so that's 6BE8. And we have a 1 indicating that it is a valid CRC. There's more to do, I think, on that front in terms of doing the appropriate thing when you see invalid CRCs, but I can't be bothered to do that today. We can leave that for next time. There's a lot of tidy up to do as well. I'm not sure if I'll subject you all to that. Yes, exactly. Yeah, a little bit of fuzzing going on there. Okay, we can get rid of all this stuff. I think what I'm going to do now is quickly look at framing and decoding. So I'm not going to do cobs today, but I'm going to try and decode decode the frame in Python. Because we have it coming in quite nicely, we can see the data is always 2 bytes for the ID. 1 byte tells you how long the data is, 1, 2, 3, and then you've got 2 bytes of CRC and then 1 valid or not valid flag. So we should be able to maintain synchronization reasonably well with this, so long as we don't see garbage data or partial frames or whatever. So let's have a go at that quickly. First up, we need to read the ID. So ID equals 2 bytes from there. Can't use the ID. What they call it in CAN. Oh, it just is called ID. Okay. Frame ID. FID. flen. And that's actually not technically the length, that is all of these bits, but just for now, let's pretend those are always there is. Pretend that remote and extended are always 0. Okay. Then we can read n bytes of data, f data. Then we have the CRC, and then f flags. Now, I don't think this read API is going to work like that, but we can try it. Okay. What do you reckon? I think it's going to blow up. Place your bets. Ooh. Oh, memory view in it. Okay, yeah. So this is actually providing us with a memory view. Oh, and read should be read one, not read nothing. So it looks like that one's okay at least. Just saying that. Give us. No, it doesn't. Still gives us a memory view. It's not going to do what I want. Being lazy. The routine is not subscriptable. Oops. Yeah, look at that. Wicked. Okay. Yep, that looks good. If we get the scope back, we can see that the CRC there is 6BE8. We got the order of the bits right there. Good. Cool. Then we can make something of the flags. So if let's do CRC valid, and then we can do if flags and XO1. No. Brain no worky. Can I do like a no yes tuple around that? unhappy, but... Oh, there you go. Cool. I think that's alright for today. I'm going to change that for decimal. Yep, brilliant. So that's kind of a basic Decode CRC validation in the FPGA, which is cool. We got no ACK yet. I think that's kind of next on the list, isn't it? Probably. Done, basic. And then I think COBS is going to be the next thing to do. Because that would be really good to have. I'm going to put this somewhere. Like that. And we can continue next time, I think. Yeah. So then, I think that's pretty much the end of today. If you've got any questions or anything, please feel free to chip in quickly before I go. Otherwise, I think I'm going to be packing up and coming back to this hopefully next week, maybe the week after. We'll see. Lots of stuff going on in my life at the moment. So yeah, that's cool. Thanks, everybody. I will see you probably next time. So yeah, thanks for watching if you have been. Thanks Omni, you as well. And yeah, that's been good progress. Thank you for your input, Omni. Bye Keystorm as well. And see you soon. Bye all.